All right, folks, it's Fast Action back in action here. On this page of notes, we're going to actually look at an application of the difference quotient. So in the last class, we practiced the difference quotient, just getting comfortable with that algebra. And then now I'm going to show you how that actually works, how that is applicable for us. And then we're not going to go much farther with it because it is a calculus extension. So it's really the first idea that you'll apply in your calculus classes. So let's call your attention to a few things on the page before I actually get into the answer. For starters, here's our formula for our difference quotient. You'll notice that it has this notation of a limit. That's really where you're going to start in your calculus classes, is with limits. So what we're going to be doing is we're going to be thinking about the values of h getting very, very close to 0, but not exactly 0. Because, of course, when we look at this function, what we know is its domain would not include h equals 0, even though we go through all of our simplification and eventually cancel that h. So recall the example that we did in class the other day where we factored and we canceled and we found a domain of all real numbers except for a particular value. Because remember, we always find the domain before we do any canceling. So our domain would exclude this 0. So what we want to understand is the behavior of this function as we choose h values that get very, very close to h. Now, on the previous video, I talked about a secant line, and I've got just a general picture here. This is not the picture of the graph that we're going to do. The previous video and the previous page of your notes has the graph of the actual function we're looking at. This is just a general graph of just a general curve here that's in blue. So if we went through the process of the average rate of change, we could find the slope of this red line, the secant line. And then just like we did in the previous page, we could write the equation for that secant line. Doesn't matter which point we would choose, as we showed in the previous video, we can get to the equation for that line that would describe the average rate of change or an approximate slope between those 2 points. Now what we're going to do is we're going to imagine these 2 points moving closer and closer and closer together, because we're going to choose smaller and smaller values of h. So as h gets smaller and smaller, these 2 points become closer and closer together, becoming almost the exact same point. So what we'll ultimately end up being able to do if we have just a single point is we'll be able to write the equation of a line that's tangent to the graph instead of secant to the graph. All right, so let's do another difference quotient example. And what we're going to start with is just our formula, so we're going to jump straight into that. So remember, when we do the difference quotient, anywhere we see an x for our first portion, people were struggling with this in class, the first part of the difference quotient is evaluating this function for x plus h. So when I first do this, I'll have my -2, and I'm going to have an x plus h squared plus an x plus h. That takes care of the f of x plus h. Then I need to subtract the entire original function. And that entire expression is over an h. The goal is to cancel that h, of course. Now, let's start expanding. So we're going to have our -2. I'll have my x squared plus my 2xh plus my h squared. It's going to get a little crowded. Plus an x plus h plus a 2x squared, because I'm distributing this negative, minus an x all over my h. Slide this up, it'll make it a little bit easier for us to follow. Now we're going to distribute that -2. So I'm going to have my -2x squared minus my 4xh minus my 2h squared, almost wrote an x there, minus my 2h squared plus an x plus an h plus a 2x squared minus an x all over an h. Once you get everything expanded, all of the remaining terms should have an h in them so that we can ultimately cancel the denominator. So my -2x squared, positive 2x squared, a positive x and a negative x. as a course of just practice, I like to go back through and just circle the parts that are left over because it helps me see it just a little bit better. So I've got a negative 2h squared minus a 4xh plus an h all over an h. I'm going to factor out the h. Negative 2h minus 4x plus a 1. A lot of students lose that plus 1 there at the end. And those cancel. So our final answer for our difference quotient is negative 2h minus a 4x plus a 1. And if I asked you to find the difference quotient, that's all you would do. Now, what we're going to do is we're going to take this and we're going to, because remember, this was our example from the previous page, we're going to let our h value equal a very, very, very small number, something so small that we really can't even imagine what this looks like. So we've got our negative h minus our 4x plus our 1. I plug in that value for h, so I have my negative 2, and it's very, very small, which is the whole idea. We want it to be so small that we wouldn't be able to picture it in our mind. And then we're also going to pick a value for x. We have to pick a point that we're actually evaluating here. So I've got that as well. So I'm going to choose an x value of 1 plus my 1. When I plug all that into my calculator, which I don't really so much need a calculator because I just imagine that 0.001, this right here, I just imagine that is just a 0 there. So what I end up getting, but I'll go ahead and write it out, is a negative 3.002. That is a slope of the line that touches our graph at x equals 1. That's what it does. That's exactly what that's telling us. So instantaneous rate of change, when it's found for a single value that we did for x equals 1, will approximate the slope of a tangent line. So to help you see this just a little bit better, we're going to take this slope and we're going to actually write the equation for the line, and then you can turn back to the previous page and graph that line, and I think you'll see how well this worked for us. So the first thing that we want to recognize is pull out some important information here. Our slope that we just calculated. Now when you go to graph it, just graph a slope of negative 3. That'll be fine. And then this point is the point 1, and then f of 1 is just putting that 1 into our function, and we get a negative 1. Writing it, I'm going to do y plus 1. I'm going to start with my point slope form. Negative 3.002. And I've got my x minus my 1. I'm going to expand all that out. Remember, when you graph this, when you turn back, you're going to actually just graph a slope of 3, up 3 over 1. Moved that 1 from the other side. So my final equation for my line is y equals negative 3.002x plus 2.002. So when you go graph this on the previous page, what I want you to do is I want you to do a y-intercept of 2 and a slope of a negative 3, and I think you'll see that you get a line that is tangent to the parabola that I've shown you on the previous page. All right, the last little bit that I'm going to show you is very, very quick. This won't take me more than probably 60 seconds. We're going to look at some different ways to analyze a graph, and the first one that we're going to talk about is continuous or discontinuous. The actual math behind continuity is much more advanced than we can cover in this class, so I'm going to give you a really, really simple definition for this and the way we're going to analyze it. So what we're going to say is this. We're going to recognize that calculus is required for a precise definition, but we can observe that a function is continuous. So we can just fill in our word here, continuous, if the graph has no gaps or holes, and this is kind of our money statement here, and can be traced without lifting the pencil from the paper. So that's it. That's all we're going to do. So you're going to put your pencil on the graph and you're going to start tracing the graph. And if you can trace the entire graph without ever picking up your pencil, that graph is continuous. That's it. That's all you have to do. You can really just do it by inspection, just by looking at it. So let's look at our other one. If I trace my graph, I start on the left, go over, I get to here, and in order for me to get to the next piece, I have to pick up my pencil and continue tracing. So that second graph is not continuous because I had to pick up my pencil. That's it. You do have a couple more things on the next page. I've tried to get this year to give you a little bit more analysis on the graphs and how to analyze some of our more difficult things. So be sure to watch that video too.